Hi, in this first video of Unit 2, we will deal with the different methods of formation of metal carbon bonds of the main group elements. Procedures for forming bonds between the elements of the main groups and carbon can be grouped into the following types: direct synthesis, transmetallation, metathesis, hydrometallation, carbene insertion, and metallation. The first one, direct synthesis, is in fact an oxidative addition. Transmetallation and metathesis are interchange reactions, and hydrometallation, carbene insertion, and metallation are insertion reactions. Let's start with the direct synthesis. This is a fairly general route to organometallic compounds that consists in the reaction between a metal and an organic halogen compound. Remember from video 1 in Unit 1 that one of the earliest organometallic compounds ever to be prepared, ethyl zinc iodide, was made in this way from zinc copper and ethyl iodide. Other organometallics prepared by this procedure are those of lithium, such as butyl lithium and Grignard reagents. There are several important factors that will affect this reaction. Those factors are the metal, the halide and alkyl group, the solvent, and the Würth coupling reaction. It is necessary to have a look at the thermodynamics of this reaction. The reaction between an element and methyl chloride to give the chloride of the element and the methyl of the element is generally exothermic and can therefore be used as a method of synthesis of these compounds. However, the mechanism of reaction and the conditions under which it takes place vary greatly from element to element. In this figure you've got here, it can be seen that in general, the main driving force of this reaction is the high enthalpy of formation of the metal halide salt that generally renders this type of reaction exothermic, with just a few exceptions, such as the reactions to prepare alkyls of mercury, thallium, lead, and bismuth. The role of the high enthalpy of formation of the metal halide salt is particularly striking for the group 12 elements, zinc, cadmium, and in some cases also mercury, whose binary methyl compounds are thermodynamically unstable because their standard formation energies are positive. Remember that we have just seen this in Unit 1, Video 3. However, the enthalpy of the direct synthesis reaction of these metals with methyl iodide is exothermic, and this is due to the high enthalpy of formation of the metal halide. The reaction with methyl iodide has to be initiated with light for cadmium and mercury, and an amalgam zinc copper has to be used in the case of zinc. As I mentioned earlier, this is, however, not true for elements of high atomic number like thallium, lead, bismuth, and in other cases mercury, which form weak metal carbon bonds. In these cases, an additional contribution to the driving force must be provided. One possibility is the use of an alloy which, in addition to the metal to be alkylated, contains a strongly electropositive element. Now let's look at the organic halide. Calculated heats of reaction of methyl halides with metals suggest that methyl fluoride should react more exothermically than the other halides. In practice, however, methyl fluoride reacts by far the most reluctantly. It is the one which reacts with more difficulty. The activation energy will almost certainly be related to the strength of the carbon-halogen bond, which is breaking. This bond is stronger in carbon fluorine and weaker in carbon iodine, and therefore the relative reactivities, the rates, usually rise from alkyl fluoride to alkyl iodide. This is another example of reactions which are thermodynamically very favored but which are controlled by kinetic factors. Regarding the applications of the direct synthesis method, we have to say that direct synthesis is usually suitable for the preparation of organometallic compounds of the most electropositive elements. Remember that these organometallic compounds will be very reactive, mainly against oxygen and water, so they must be handled under an inert atmosphere of nitrogen or argon. On a laboratory scale, the derivatives of lithium, magnesium, and aluminium, which are very important as synthesis intermediates, are generally prepared by this method. The most important metal in group 1 is lithium. The metal has to have a large contact surface, and sometimes impurities of sodium catalyze the process. Organolithium compounds can be prepared by reaction of lithium metal on alkyl or aryl halides in ethyl ether or hydrocarbon solvents, pentane, hexane, etc. Chlorides are preferred over bromides, and with the important exception of methyl iodide, alkyl iodides are not used because they react very quickly with the organolithium derivative just formed, given the Würth coupling. This coupling is less important in the aryl halides. Therefore, aryl bromides and iodides can be used to prepare the corresponding alkyl and aryl organometallic derivatives. In group 2, the most used metal is magnesium to prepare Grignard reagents, although lithium is more reactive. Magnesium must be very pure, and as the surface of magnesium metal is covered by a passivating oxide film, the magnesium has to be activated by adding a trace of iodine, which forms magnesium iodide. This compound is soluble in the solvent, an ether, and dissolves to expose an activated magnesium surface. A special type of magnesium called Rieke can also be used, which is in the form of highly reactive small particles of magnesium with large surface area. It is prepared by reducing magnesium dichloride with lithium metal. Magnesium reacts with alkyl and aryl halides in ether solvents, always under anhydrous conditions, to form Grignard reagents. This reaction is an oxidative insertion of magnesium into the carbon-halogen bond, which involves oxidation from magnesium 0 to magnesium 2. Ether solvents like the ethyl ether, tetrahydrofuran, THF, dimethoxyethane or dioxane are most suitable for the preparation of Grignard reagents. It is because they are not only unreactive with magnesium, but also dissolve and stabilize the Grignard reagents by forming Lewis acid-base complexes. These ethers can coordinate the organometallic compound through the lone pairs of the oxygen, so they can thus stabilize Grignard reagents. Grignard reagents react with protic compounds like water, alcohols, thiols, etc. Hence, the reaction must be carried out under anhydrous conditions, avoiding moisture. These reagents must not be exposed to air, as they also react with oxygen by giving peroxide species, which are converted to corresponding alcohols during hydrolytic workup. To avoid this, it may be preferable to carry out the reaction in nitrogen or argon atmosphere. Grignard alkyls are prepared from the corresponding chlorides, bromides, or iodides. Alkyl chlorides, however, are usually used because they are cheaper and, although they react more slowly with magnesium, secondary reactions such as Würth coupling are avoided. Vinyl bromide and bromobenzene can be converted to the corresponding Grignard reagents by reacting them with magnesium metal in anhydrous THF. The second method we are seeing to form metal-carbon bonds is transmetallation, which is an interchange reaction. Transmetallation is the reaction between a metal and an organometallic compound, or between two organometallic compounds in which the interchange of metals takes place. This method depends on the difference in the free energies of formation or formation enthalpies of the two organometallic compounds. Endothermic or weakly exothermic organometallic compounds should be the most versatile reagents in these reactions. Thus, mercury, thallium, lead, and bismuth are used. Of these, organomercury compounds, which are easily prepared, are the most commonly used, but do not forget that they are very, very toxic. Other elements that react satisfactorily with the dialkyl and diaryl mercury include the alkaline earths, aluminium, gallium, tin, lead, antimonium, bismuth, selenium, and tellurium. Another example of transmetallation reaction is the synthetic procedure to obtain vinyl lithium, starting from phenyl lithium and tetravinyl tin. Precipitation of tetraphenyl tin shifts this equilibrium to the right, and good yields of vinyl lithium are obtained.